Chapter 14 is called Chemical Kinetics. As we've discussed in the past, there's five main focuses of study that they currently use on the AP exam. One of those areas of study, which we studied back in Chapter 5, deals with thermochemistry. Sometimes we refer to them as just thermodynamics. That's one focus of the AP exam. Another focus of the AP exam is chemical equilibrium. A third focus of the big five is acids and bases. The fourth is electrochemistry. And the fifth is right here, right now, kinetics. Now, like I've said, we've talked a little bit in Chapter 5 about thermochemistry, but we've not talked about equilibrium. We've talked very little about acids and bases. There's much more to come in terms of acids and bases, and we have not talked about electrochemistry at all. So this is really our first big jump into kinetics. We've, like I said, a little bit here, but there's much more of this coming. So kinetics is the first of the big five that we're really going to focus on for the AP exam. So we're going to talk about what chemical kinetics is. We're going to talk about some of the factors that affect the rate meaning speed, of a reaction, and then we're going to look at a few problems. So in chemistry so far, we've talked about the formation of a substance given a set of reactants. If I say H2 plus O2, hopefully you can figure out that that makes water. But not only is it important to know what is formed, but another thing that's also important sometimes is how quickly or how slowly a reaction actually does occur. And that's what kinetics is all about. It's about the area of chemistry that studies the speeds or the rates of a reaction. So first of all, let's talk about some of the things that can affect how quickly or slowly a reaction happens. One of them is the physical state. By that, solid, liquid, or gas, or if it's dissolved in water, aqueous. The more readily that things can react with each other, the faster they react. So the state that they're in will certainly affect that. Another thing, if it is dissolved in the water, is the concentration. The greater the concentration, the faster the reaction will tend to go. And that will certainly, as concentration increases, the frequency with which the molecules collide also increases, which allows the rate to also increase. The third one is the temperature at which the reaction occurs. Typically, the higher the temperature, the faster the things are moving because they have an increase in their kinetic energy, so they're going to hit each other more often. And then number four is what's called a catalyst. Catalysts are things that do affect reaction rates, but they themselves are not used up in the reaction. And this chapter is basically a summary of all four of those things. This chapter is going to be about those four different things that affect reactions. So we'll get into much more detail about each of those. So when we talk about how quickly or slowly a reaction occurs, what we call it a reaction rate. And that is simply the rate at which the reaction happens. The way that we determine that is we check the change in the molarity over the change in time, usually measured in seconds. So one of the units that we use for measuring the speed of a reaction is how the concentration changes over a certain amount of time. So we can talk about how, like if we have A plus B makes C, we could say A is going down by 3 molar per second. And notice we put the negative there because it's going down. Or we could say that C is going up by, 2 molar per second or something like that. So the reactants are always going down. The products are always going up. So here we see a reaction where the red spheres are becoming blue spheres. If the red spheres are equal to A and the blue spheres are B, then we've got A becoming B. And if we start with A being 1 molar, at the very beginning there is 1 molar of A and no B present at all. And let's say at time 20 seconds there's 54 molar of A and 46 molar of B. And then at time 40, blah, 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 blah. if we wanted to calculate how the A is changing over time, we could do it in terms of A disappearing from 1 to 0.54 or 0.54 to 30. Or we could do it as B appearing from 0 to 0.46 or from 0.46 to 0.70, depending on which time you wanted to focus on. So if we were talking about with respect to the appearance of B, we would take the change in concentration at a certain point minus the concentration at another point, and then use those time factors. So as we know, as we've learned with concentration, when you put square brackets around something, that represents the molarity. So this is the change in the concentration of B in terms of molarity. So it's the change in the molarity of B over the change in time. So we would put those numbers into the equation. We could, again, it doesn't matter at what point we would use, but then we could also do the same thing for A with the disappearance of A. So as we know, as a reaction occurs, the reactants or the amount of the reactants goes down. So as you start using up A, there's less and less A to react and turn into B, and so forth. The concentration of B obviously is going to go up. So as a reaction happens, it starts to proceed slower. So the decrease in the concentration of the reactants causes the rate to decrease throughout the rest of the reaction. So if we are looking at a graph of that, we might see right away, the concentration over time is going like this. And so many times, if this is time down here, and this is the concentration starts to drop very quickly right away. But then as more and more of it disappears, it goes a little slower, and it goes a little slower until it doesn't change really at all. So here is a reaction where you've got C4H9Cl reacting with water to make C4H9OH and HCl. And what they've done here is they've shown this. So right away you can see this slope here is pretty steep. But after 900 seconds, so 60 into 900 goes 15 times, after 15 minutes, that slope isn't nearly as steep because there's less of the C4H9 floating around in there. There's more of this floating around in there. So what we can do, though, is at any point on that graph, we can make a tangent line. And if we use that tangent line for, say, right here, we can figure out, well, what's the change in C4H9Cl from here to here? What's the change in time? And what that would do is that would tell us the rate at that very specific moment during that reaction. So the instantaneous rate is determined from the slope using a tangent line of the curve at the point of interest. So throughout this chapter, we've pretty much talked about two rates. We've talked about calculating an average rate, and we've talked about getting an instantaneous rate. The instantaneous, like we said, is you get that from the tangent line, instantaneous. And the average is you take your 2 points and you calculate the average between the two of them. Okay, now when a reaction begins, we're at time 0, and obviously that's at the very beginning of the reaction, so we call that the initial rate of the reaction. Okay, and that when we refer to the initial rate, we're referring to the instantaneous initial rate. So as it says right here, the term rate is going to mean the instantaneous rate unless we call it something else. So the average rate is from one time period to another. The instantaneous rate is the rate at a given point in time at that very instant. So we've seen two reactions. We've had A make B, and then we've had C4H9Cl becoming C4H9OH with some water involved there. Okay, and what we've seen is that 1A made 1B. One of these and one of these made one of these and one of these. But many times, as we know in chemical reactions, the stoichiometry is not the same. You may not have one here. You might have a 1, a 2, a 3, and a 2, let's say. So things are going to change, such as HI decomposing and forming H2 and I2. When that happens, for every 2 of these that decompose, you get 1 hydrogen and 1 iodine. So when we talk about things disappearing as opposed to things appearing on the other side, mathematically we write it like this. Notice that the coefficient for the balanced equation right here comes right down here. These coefficients are both 1. So notice that we don't write 1 over 1 here because it's the same thing as writing nothing. So basically, if you take the rate, this right here is the rate of disappearance. Rate of disappearance for HI. If you take 1/2 of that rate, so you can see that here, 1/2 times the rate of disappearance of HI, that will equal the rate of appearance of hydrogen. And that makes sense. For every 2 of these that decompose, you only get 1 hydrogen and 1 iodine. So if you take 1/2 of the rate of HI, you get the rate of appearance of hydrogen and oxygen. So a very simple way to look at that is these small letters here are the coefficients. The way that you can compare what one reactant is going to do as compared to another reactant or a product is simply taking the coefficient, putting it over or under 1, and ending up with your ratio of 1 to the other. So here's an example of this. If the initial rate of appearance of O2, so the rate of appearance of O2 is 6 times 10 to the negative 5th molar per second, what is the value of the initial rate of disappearance of ozone, which again is O3? Okay, so we know that 1/2 the rate of O3, and again, we could write it the fancy way, the change in the concentration of O3 over the change in time, but all that means is the rate of O3 equals 1/3 the rate of O2. And so what we find is that we already know the rate of O2, it's right here. So the rate of O2 we're going to substitute in right here. So you get 6.0 times 10 to the negative 5th. And now what we're trying to solve for is we're trying to solve for the rate of O3. So we need to get rid of this 1/2. To get rid of that 1/2, we multiply both sides by 2. So that's gone. So the rate of O3 is equal to, now 1/3 times 2 is just 2/3, so we could change that 1 to that 2, is 2/3 of 6 times 10 to the negative 5th. So the rate of O3 equals 2/3 of 6 is 4, so 4 times 10 to the negative 5th molar per second. Now, again here, is it positive, is it negative? It doesn't really matter, but what is the value of the initial rate of disappearance of O3? So they're saying it's disappearing. You can't have something disappear at a negative rate, so they're saying it is negative, we know that. So it's disappearing at a rate of 4 times 10 to the negative 5th molar per second. Okay? So that's something that you definitely need to be able to do. That if they give you one reactant or one product, you need to be able to take that information and you need to be able to figure out what any other reactant or product would also be disappearing or being created at that same rate. So let's say, let me get rid of this business here. Let's say we have a reaction that is 2 N2O5s becoming 4 NO2s plus O2. And they say the rate of decomposition of N2O5, so N2O5, it's decomposing at 4.2 times 10 to the negative 7th molar per second. What is the rate of appearance of NO2? So it appears at what rate? And then also, what about O2? What rate is it appearing at? So again, let's take our balanced equation. Let's work on NO2 first. So we're going to say 1/2, because of the 2, the rate of N2O5 is going to equal 1/4 the rate of NO2. So then we can take our value for N2O5, place it into here, 4.2 times 10 to the negative 7th. To get the rate of NO2 by itself, we got to multiply both sides by 4. So basically times 4, 1 times 4 is 4, so it's 4/2, which is 2. Therefore, the rate of the appearance of NO2 is going to be double, 8.4 times 10 to the negative 7th molar per second. Okay, for oxygen, it'd be very similar. It would be 1/2 the rate of N2O5 equal to 1/1, because there's nothing in front of the O2, the rate of O2. 1/1 is just 1. So the rate of O2 is just equal 1/2 the rate of N2O5. So we take the rate of N2O5, we cut it in half. 4.2 times 10 to the negative 7th, half of that is just going to equal 2.1 times 10 to the negative 7th would equal the rate of O2. Okay, so anytime you know the rate of one reactant or one product, you can use the coefficients from the balanced equation and you can convert to the rate of appearance or disappearance of other reactants or products. Okay, there's your objectives. Did we cover those? Yes, hopefully we did. There we go. What you need to do is in this section, there is a little section about Beer's law, which is an equation that looks like this. Capital A equals little a times B times C. Find that on page 581. There have been questions on the AP exam about that, and this is the only spot in the book where they actually do talk about it. And then do problem 88A on page 624, and that again is about that equation right there. And then your homework actually involving this information from the chapter is right here. And then these 4 questions right here also deal with what we just talked about. And then 5A is the one that deals with Beer's law. And for all of you getting excited about beer, don't worry. It's not actually about beer. So we'll talk about these tomorrow in class.